Hi everyone. So this video is intended to cover the ideas in chapter 11.4, which is the comparison test and limit comparison test. What I want to do with this video is to go back through the theorems and then do some illustrative examples of what the theorems are about and why we use them that way. So I'm going to start by looking at the comparison test. And the big idea with the comparison test is the observation that smaller than a finite quantity is finite. So the big theme here, if this could be said to have a theme, is that smaller than finite is finite when we're working with positive quantities, which we are here. So as an illustration, consider the function or the series 1 over n squared plus 1. So 1 over n squared plus 1 we should suspect is a convergent series because as n gets large, 1 over n squared plus 1 starts to look more and more like 1 over n squared because the lower order terms in the denominator just don't matter anymore. When you put n equals a billion in, a billion squared plus 1 and a billion squared are pretty close to each other. So we should suspect that this series probably converges because its long-term behavior looks like a p series with p equal to 2, right? So this is a p series with p equals 2, and so it's convergent. And so because the long-term behavior of the series we're interested in is like the long-term behavior of a series we know about, we suspect that the behavior should be the same. So this is what the comparison test is supposed to get us. And the explicit comparison we're going to make here is, since n squared plus 1 is bigger than n squared for all n larger than 1, then when you take reciprocals, you get the reverse relationship. So the idea here is that any partial sum of the series with 1 over n squared plus 1 has to be less than or equal to that same partial sum of the series 1 over n squared. So what I'm saying is that because 1 over n squared plus 1 is less than or equal to 1 over n squared, it also must be the case that 1 over 1 squared plus 1 plus 1 over 2 squared plus 1 plus 1 over 3 squared plus 1 and so on up to 1 over n squared plus 1 must be less than or equal to 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared up to 1 over n squared. That is, each term in this series, each term in that series is smaller than the corresponding term in this series. And so what that means is that this partial sum, say we call this Sn, and just for kicks we'll call this sigma n, for any n, the partial sums of the sequence we're interested in are less than the partial sums of the sequence we know about. And so the conclusion that we make is, well, since that was true for every possible n, it must also be true in the limit, which is to say that the sum from n equals 1 to infinity of 1 over n squared plus 1 must be less than or equal to the sum from n equals 1 to infinity of 1 over n squared. And this was convergent, and so was finite. And since this is a bounded sequence of positive numbers that increase, it must have a limit, and that limit must be smaller than the limit of the sum of the 1 over n squareds, which is finite. And so because this is finite, this must be. And therefore, we know that this must converge. And ultimately, that's what the comparison test is about. Smaller than something finite means that you're finite, and thus convergent. Larger than something infinite means you're infinite, and thus divergent. Okay, so if you have two series with positive terms, and the positive is important here because otherwise you don't have the bounded increasing sequence has a limit theorem to rely on. So if you have two series with positive terms, then one, if you have a convergent series, so say the BNs converge, and the terms of the other series are smaller than that, then this series also converges. That is to say, smaller than something finite means you're finite. 2, if the sum of the BNs diverge, and the second sequence or second series is larger, well, larger than a divergent series is divergent. Okay, that's the comparison test. So I'm going to do a quick couple of examples here. Partly because what I want to point out is that frequently what we're doing when we're dealing with comparison tests is we're comparing to series that we already know the behavior of because of the form of the comparison. So the library of examples that we're going to be comparing to are typically p-series and geometric series. So typical comparisons involve p-series and geometric series, because we know when those series converge and diverge. So let's look at a couple of quick examples. So one typical sort of thing would be to look at a series like this. So say that we had n over n to the fourth plus 1. Okay, so n to the n fourth plus 1, the very first thing I should do when I look at a series, is especially a series of rational terms like this, is to try to figure out what I believe about what the behavior of the series is. And when I look at this, I believe it converges. And the reason is, as n goes to infinity, the terms of this series end up dominated by the leading terms. So the n is the only term in the numerator, that lives. And the dominant term in the denominator is n to the fourth. So in the limit, these start looking an awful lot like n over n to the fourth, which is 1 over n to the third. And things that look like 1 over n to the third converge, right? Because this is a p-series with p equals 3. And so convergent. So the observation that I have to make is that n over n to the fourth plus 1 is less than or equal to n over n to the fourth, because n to the fourth plus 1 is larger than n to the fourth. And so throwing away the 1, I'm not really throwing it away, but I'm estimating it by saying, well, n to the fourth plus 1 is bigger than n to the fourth. And so if I take the reciprocal, I get something smaller. Since this is true, and n over n to the fourth is 1 over n to the third, and the sum of 1 over n to the third converges, then the sum of n over n to the fourth plus 1 converges by comparison. Okay, so these sorts of estimates are typical of this type of mathematics, where the behavior of a series is really dictated, especially a series with rational terms. The behavior of a series is dictated entirely by what its long-term behavior is. And so we're not really throwing away a 1 or getting rid of it and just restricting our attention. We're using an inequality to replace that. Or we're looking at infinity, or looking at asymptotics and figuring out, okay, what are the dominant terms in the numerator and denominator of some fraction? Okay, another example of where the comparison test is used. So you could have a series like this. So this series, of course, doesn't have a limit as, well, the numerator anyway doesn't have a limit as n goes to infinity, because cosine squared of n flops around back and forth between 0 and 1 forever, right? It's a cosine, but with integers plugged into it. But the observation that you can make here is that cosine squared of n is stuck between 1 and 0. Right? The range of a cosine function is between -1 and 1, so if you square that, you get a function whose range is trapped between 0 and 1. Well, what that means is that we can use this part of this inequality to produce a comparison. Since cosine squared of n is less than or equal to 1, it must be the case that cosine squared of n over n squared is less than or equal to 1 over n squared. And this series is a convergent p-series with p equals 2. And so this sum must converge by the comparison test. Okay. So typical sort of argument here when you've got things not that have limits, but that or dominant terms, but things that you can estimate because the functions are bounded. So the point here is that this function is a bounded function. And since it's bounded, that gets you an inequality automatically. So with bounded functions, you can always use comparisons. Now I'm going to write down a function that is going to complicate the comparison test because it seems like it should work, but it doesn't. And we want to come up with a method that can handle these sort of cases. So consider the example that looks like n over n to the fourth minus 1. So this one, you think should also converge, if you think about it for a second, because as n goes to infinity, n over n to the fourth minus 1 pretty much looks like n over n to the fourth. Again, subtracting 1 from n to the fourth doesn't really change it that much when n is on the order of a billion, say, which looks like 1 over n to the third. And that's a convergent p-series. And so you suspect that should also be, because its growth is the same, its behavior, its asymptotic behavior. As you let n run to infinity, the terms of this series look like the terms of this look like the terms of this. They're very similar to each other. And so since they're so similar, you suspect that because this converges, this must also converge. The problem is the comparison test doesn't work because n over n to the fourth minus 1 is bigger than n over n to the fourth. And bigger than convergent doesn't give you any information. So our comparison fails. We can't conclude anything about the series because we don't have something smaller than something finite. We have something bigger than something finite. And bigger than finite could be infinite. So this is a no information case. And that's frustrating because we believe that it should have a solution because you can see that the order of the series is the same as the order of the series 1 over n to the third. So the solution to this is a test called the limit comparison test, which means instead of trying to come up with an inequality, what we'll do is we'll compare the asymptotic behavior of the two series. And if they have the same asymptotic behavior, then they should either both converge together or they should both diverge together. So this is what the limit comparison test says. So again, if you have two series with positive terms, and the limit as n goes to infinity of the ratio of the terms converges to some number c with C being trapped between 0 and infinity. So C can't be 0 and C can't be infinity. We know it must be positive because all the terms of the sequence are positive. So if C is a non-zero, non-infinite number, then either AN and BN converge together, both converge, or AN and BN both diverge. Okay. So again, in the limit, what we're saying is that if we compare what their terms are doing, if we end up with a constant, it means that they're going to infinity at the same rate. And that means that they look the same, essentially, as n goes to infinity, which tells you that if one converges, the other must. One of them is tending to 0 fast enough to converge, then so does the other one. So let's look at our example. So we had the sum from n equals 1 to infinity of n over n to the fourth minus 1. And we've already decided that this kind of looks like the sum of 1 over n to the third. Because as n goes to infinity, this is dominated by this. Okay. So that gives us what we want for our comparison. So let's look at the limit as n goes to infinity. There's no reason to choose one over the other in this test, but we'll let an be the series that we're testing. So n over n to the fourth minus 1, and then we'll divide it by the series that we already know about, which is 1 over n to the third. And then some basic mathematics should get you n to the fourth over n to the fourth minus 1, and that limit is 1. 1 is between 0 and infinity, and that means that the sum from n equals 1 to infinity of n over n to the fourth minus 1 converges by the limit comparison test. Okay. So limit comparison tests basically work anytime you've got combinations of things that look like polynomials or even fractional powers, right? So mixtures of polynomial type objects that have dominant terms typically can be thought of as being on the order of something that we know, typically P series. Okay, so that's a quick summary of the content of chapter 11.4. The way to get a handle on how to choose the comparison series and the feel for when to use comparison versus limit comparison, that's going to come from doing lots of exercises. And so you should go beyond the homework and do as many exercises as you can bear to make yourself do to master this stuff, because the more repetition you have, the more readily you're going to identify the pattern when you see it on, say, an exam. So I'm going to leave it here. If you've got questions about this stuff, please feel free to contact me, and we'll move on next time to talk about alternating series. All right, take care.